So far, we've been looking at how to understand costs that have already happened. But now we're going to start looking at some techniques to use that information to predict the future. In this section, we're going to examine how costs behave. In the real world, costs behave in lots of different ways, but generally, we can think of them as falling into one of three basic categories: variable costs, fixed costs, and mixed costs. Variable costs get their name because we expect these costs to vary as the firm's activity level changes. So variable costs like direct materials or direct labor increase as the firm's activity level increases. But we expect the variable cost per unit to stay about the same as the activity level changes. Fixed costs, like factory rent, get their name because we don't expect them to change because of a change in the firm's activity level. Of course, that doesn't mean that they never change. For example, the firm could get a rent increase on the factory, but it didn't happen because the firm was a little busier this period than it was last period. So a firm's total fixed costs stay the same as the activity level increases. But that means that the fixed cost per unit actually decreases as the activity level increases because that cost can be spread out over more units. Some costs aren't strictly variable or fixed. For example, a utility bill has two kinds of charges: a line charge just for having electricity, and then a usage charge that depends on how much electricity is used. These costs are called mixed costs because they have both a fixed and a variable component. Let's take a closer look at how costs in each of these categories behave. Here's a graph of total variable costs at different levels of activity. The x-axis is always some measure of activity. It could be the number of units, or the number of machine hours, or the number of inspections, or any other activity measure that the firm is considering. And the y-axis is always dollars of cost. The total variable cost line always passes through the origin. That means, for example, that the firm would expect to have 0 direct materials costs when it's making 0 units. The slope of the total variable cost line is the variable cost per unit, in this case 80 cents per unit. And we can see that the slope stays the same as the activity level increases. That's what makes this a straight line. So this graph shows that the variable cost per unit stays the same as the activity level increases. The graph also shows that the total variable cost increases as the activity level increases. For example, at 80 cents of variable cost per unit, if the firm expects to make 1,000 units, it would predict $800 of this variable cost. But if the firm expected to make 2,000 units, it would predict $1,600 of the variable cost. And if the firm expected to make 3,000 units, it would predict $2,400 of this variable cost. Now, let's look at how fixed costs behave. We can see from the graph that the total fixed costs stay the same as the activity level increases. But the fixed cost per unit actually decreases as the activity level increases. For example, if the firm expects to make 1,000 units, it would divide its total fixed cost by the 1,000 units, which means that each unit would carry $3 of that fixed cost. But if the firm expected to make 2,000 units, it would divide the $3,000 fixed cost by 2,000 units. So each unit would carry only $1.50 of that fixed cost. And if the firm expected to make 3,000 units, it would divide the $3,000 total fixed cost by the 3,000 units that it expected to make, and each unit would only have to carry $1 of fixed cost. So as the firm's activity level increases, each unit carries a smaller share of the total fixed costs because those fixed costs get spread out over more units. This graph shows what a mixed cost would look like. Remember that a mixed cost has both a fixed component and a variable component. The fixed component is the height that the mixed cost intersects the y-axis above the origin. And that part, in this case $3,000, is going to be there regardless of the firm's level of activity. But on top of the fixed component, the total mixed cost also has a variable component, in this case 80 cents per unit. For example, to find the total mixed costs, if the firm expects to make 1,000 units, we would go up on the graph from 1,000 units and across to the y-axis. And the total mixed cost would be the 80 cent per unit variable portion times 1,000 units plus the $3,000 fixed portion for a total of $3,800. If the firm expected to make 2,000 units, we would go up from that activity level to the total mixed cost line and across to the y-axis. So the total mixed cost would be the 80-cent per unit variable portion times 2,000 units plus the $3,000 fixed portion for a total of $4,600. And if the firm expected to make 3,000 units, we would go up from that activity level and across to the y-axis. So the formula for the total mixed cost would be the 80-cent per unit variable portion times 3,000 units plus the $3,000 fixed portion for a total of $5,400. So total mixed costs do increase as the activity level increases, but not in direct proportion to the activity level, because as the activity level increases, each unit carries a smaller portion of the allocated fixed costs. Here are some questions to think about. The first question is, what is the behavior of direct materials and direct labor? Are they variable costs, fixed costs, or mixed costs? You're right, they're variable costs because they don't exist if we don't make any units, and they increase in proportion to the number of units that we make. What about factory rent? Is it variable, fixed, or mixed? Correct. It's a fixed cost because it doesn't change with the number of units the firm makes. That doesn't mean that the landlord is never going to give the firm a rent increase. It just means that the rental cost is not dependent on the number of units produced. What about factory electricity? Is it variable, fixed, or mixed? This is a harder question. Factory electricity is actually a mixed cost because it has a fixed component called the line charge, and then on top of it, it has a variable component called the usage charge. What about machine depreciation using the straight line method? You're right, it's a fixed cost because depreciation is the same each period under the straight line method, regardless of how busy the firm is. What about machine depreciation using the units of activity method? In this case, depreciation would be a variable cost because the units of activity method determines depreciation based on an activity measure, like how many machine hours are used or how many soda bottles are capped. Therefore, the depreciation will increase whenever the activity level is higher, and it will decrease whenever the activity level is lower. Another important concept to understand how costs behave is the idea of a firm's relevant range. That is, the range of likely activity levels for that particular firm. In the relevant range, the fixed costs are going to remain fixed. In other words, the firm isn't going to build a new production plant or get rid of an old production plant. And the variable cost per unit also remains the same. Because of that, we can approximate these costs with straight lines. Here is a diagram of a firm's typical production cost function, and you can see that it looks nothing like a straight line. It's certainly not a straight line at the lowest end of activity, but the firm is never going to be operating there. It's also not much like a straight line at the highest level of activity, but the firm isn't going to be operating at very high levels either. But in the middle, in the range of the firm's likely activity levels, it looks a lot like a straight line, as shown here. And we can treat the cost behaviors as a straight line within this range. So this firm's relevant range would be approximately as shown in this diagram. Now the question is, how can we determine the formula for this straight line? There are several ways to understand mixed costs. One way is to use regression analysis, but that requires a computer and some statistical software. A much easier way that's pretty good for approximating costs is the high-low method, and that's what I want to show you now. Let's assume that XYZ wants to understand its machine costs so that it can predict how much it will cost the firm to operate its machine in each period. The firm believes that machine costs are related to how many hours the machines run. So it collected some data over 6 months. That data includes how many hours the machines were used in each month and how much it cost the firm to run the machines. Now the firm wants to use the high-low method to develop an equation so that it can predict its machine costs at any level of activity within the relevant range. So, the first thing the firm has to do is to find the high and the low activity levels. So, we look down the list of machine hours and we find that June has the highest activity level. And then we can look across and find the cost to run the machines in June. we might have been tempted to pick February because February has higher machine costs than June does. But our model says that machine hours create machine costs, not the other way around. So we disregard February and stick with June because it has the highest activity level. April has the lowest activity level and also the lowest machine costs, as shown here. Once we have the high point and the low point, we can disregard all of the other months. Now that we've found the high point and the low point, we want to find the formula for the straight line that connects those points. That's going to be our mixed cost line. The formula for a straight line is y equals a plus bx, where b is the slope of the line. The formula for the slope of any straight line is delta y divided by delta x, like this. That means the change in cost between the high point and the low point divided by the change in activity between the high point and the low point. So we look back at our high point and low point for cost and then divide that by the high point and the low point for activity. Now it's just a matter of cranking out the numbers. Here's the difference in cost between the high point and the low point divided by the difference in machine hours between the high point and the low point. When we divide this out, we get 10.40. In other words, this firm estimates that it costs them $10.40 of machine costs per machine hour used. And we can plug that into our formula for B, the slope of the line. The next step is to find the y-intercept. That is the place where the mixed cost line crosses the y-axis, and that point represents total fixed costs. To find that point, you need to look at either the high point, that is data from June, or the low point, that is data from April. In this case, I chose June, but it would work equally well with April. Once we've chosen either the high point or the low point, we're going to substitute the number of machine hours used in June for X and the total cost to service the machines for Y, like this. There's the total machine hours for X. There's the total cost for Y. And that leaves us with one equation and one variable. So we know that we can solve for A, which represents the y-intercept. So we multiply the variable cost per machine hour, $10.40, times the number of machine hours in June. And then all we have to do is subtract that number from both sides, and that will tell us the fixed cost. Like this. So now we know that for this particular firm's machining costs, the total fixed cost is just under $7,000. Now that we know the variable cost per unit and the y-intercept, we can plug these values back into our basic equation for a straight line, y equals a plus bx. We substitute the total fixed cost for A, and we substitute the variable cost per machine hour for B, and that gives us an equation that will predict how much it will cost to take care of the machines at this firm for any level of activity within the relevant range. We can interpret this formula to mean that the total machining cost is equal to $6,976, the fixed cost, plus $10.40 per machine hour times whatever activity level we're interested in within the relevant range. For example, let's suppose that the firm estimates that it will use 480 machine hours next period, and it wants to know how much that's likely to cost to take care of the machines. We start with our formula that we generated on the previous slide, where we've substituted total fixed cost for A and the variable cost per machine hour for B. Now we substitute 480 machine hours for the activity level, and that gives us an equation that will estimate the total cost to take care of the machines. So we multiply the activity level, 480 machine hours, by the $10.40 variable cost per machine hour, and then we add that to the total fixed cost, and that gives us our best estimate of the total cost. This is the end of part 1 of this chapter.